Welcome back, students. In this video, I'm going to show you how to model Mealy and Moore state diagrams. We can model a state diagram easily in Verilog. There is no need to have the circuit implementation. In other words, I don't really need to have the next state and output equations to model the state diagram. Here's an example of a Mealy state diagram as shown below. You can see that the output appears on the transition, on the arc. So we have here a state diagram for the 111 sequence detector. Okay, so this state diagram is going to detect the sequence, the 111 sequence. It can detect 3 or more ones. We have seen the state diagram in a previous presentation. So I only have 3 states. And we have the state assignment done on the state diagram. So S0 is defined here to be 0, 0. S1 is 0, 1. And S2 is 1, 0. So let us see how we can model the state diagram directly in Verilog. This is explained in the next slide. Here's my module, which is called Mealy 111 detector. Okay, it has 3 inputs, X, clock, and reset. I have a third input, reset. It's very important to reset back to state 0, 0. There is only one output, which is called Z. This is the output Z that's going to detect when it will output 1 when we detect 3 or more ones. Now, we would like to model the state diagram directly in Verilog. In order to do this, I can describe the behavior of the flip-flops. I can describe the behavior of the next state logic, and I need to describe the behavior of my output logic. So we're going to define here state. Now, state here consists of 2 bits. This is my present state. Notice that we have 2 bits here, bit 1 and bit 0. And this is my next state. This next state means the input to the flip-flops. So the state appears inside these circles here. For example, 0, 0, 0, 1, or 1, 0. These are my states. Now, in order to describe the flip-flops, I can write an always statement. This always statement is sensitive to the positive edge of the clock. Now, if we have a reset, then this will take me back to state 0, 0. So I can write an if statement here, then state becomes 0, 0 if reset. Now notice that this reset is synchronous reset. It is synchronized with the clock. Why? Because the always statement is sensitive only to the positive edge of the clock. So only when we have the positive edge of the clock, then we can change the state back to 0, 0 if we are resetting. So the reset will happen only at the positive edge of the clock. If we are not resetting, then state becomes next state. Okay, that's how we make a transition from state to the next state. It means that the output Q of the flip-flops becomes the D input of the flip-flops. So we are describing 2 flip-flops with the help of one always statement. Next, we need to describe the next state logic according to the state diagram. So I'm going to write an always statement. Now, this always statement is sensitive to all the inputs that appear inside the always statement. So I'm writing here at star because this next state logic is a pure combinational logic. Notice that this always statement will be sensitive to X because you can see that X here is red inside the case statement. It's also sensitive to the present state. You can see that state here appears also inside the always statement. Okay, so therefore it is sensitive to state as well as to X. But you don't really have to write here state comma X. You can just write it as a star, and the compiler will understand that this star means the state and the input X. So these are inputs to this always statement. So what this always statement is describing is the next state. So the next state depends on the present state as well as the input X. The present state can be either 0, 0 or 0, 1 or 1, 0. there is also a default case, okay, that's actually for the unused state, okay, when the state is equal to 1, 1. So what we would like to describe here is the next state. So we are describing the state transitions as given in the state diagram. So when you are in state 0, 0, and the input x is equal to 1, so if x is equal to 1, then this will take you to state 0, 1. Then this will be the next state. However, if the input x is equal to 0, okay, if you are actually in state 0, 0, and the input x is equal to 0, this will take you back to state 0, 0. So this is actually the description of the next state when the present state is 0, 0. So the next state will depend on the input x. Similarly, when the present state is 0, 1, that will be my second line here. Okay, that's actually when the present state is equal to 0, 1. Then if the input x is equal to 1, then my next state will be 1, 0. So we have this transition here, okay, from state 0, 1 to 1, 0 when the input x is equal to 1. However, when my input x is equal to 0, we'll have a transition from state 0, 1 back to 0, 0. So my next state will be 0, 0. Finally, if you are in state 1, 0 and the input x is equal to 1, you make a transition from 1, 0 back to 1, 0. But if the input x is equal to 0, this will take you back from state 1, 0 back to 0, 0. This is described on this line. So this is how we can describe the next state without writing any equation. We can just describe it with a conditional expression as indicated inside the case statement. Now I need this default case. Why do I need this default case? Because we have actually a state which is not used, which is state 1, 1. If we enter the state, okay, for whatever reason, for example, when we power on the circuit and we enter the state, or because we have a malfunction, I would like to ensure that my next state will be 0, 0. So if for some reason we enter this unused state, which is here 1, 1, I would like to ensure that my next state is 0, 0, regardless of my input x. Now, this always, so we have seen that this second always statement describes the next state logic, and it describes the transitions between the states as shown in the state diagram. Finally, for my output, I need to describe also my output logic. Now, this can be described very easily with a continuous assign statement. So I can say that z is equal to the output 1, okay, when the present state is equal to 1, 0, and the input x is equal to 1. So I can describe it, okay, with this expression, state equal to 1, 0, and x. It means that x is equal to 1. If this is the case, we get the output z is equal to 1. Otherwise, we have the output z is equal to 0. So this is how I break down the description of a state diagram into 3 parts. I have the first always statement that describes the flip-flops, okay, with a synchronous reset. The second always statement describing the next state. And finally, my continuous assign statement describing the output z. I can also describe the output z with an always statement. I can always do this, okay? I can use an always statement, which is sensitive to state and x, and I can describe this output z with a procedural assignment rather than with a continuous assignment. So that will be also another way to describe the output z. Here's another example. Let us see how we model a Moore state diagram. Now, this Moore state diagram is for a comparator that we have seen in a previous presentation. So the inputs here are A and B. So I would like to compare here A and B. So these are bit serial. We present each bit. Okay, each cycle we have 1 bit of A and 1 bit of B. Here is my clock input and here is my reset. The outputs are, we have 3 outputs. We have greater than, we have less than, and we have equal. Okay, so these are the 3 possible outputs of this comparator. Again, we have to define here the present state and the next state. So we have here only 3 states. So these are defined by 2 state bits, 0, 0, 0, 1, and 1, 0. Okay, so 0, 0 indicates equality, 0, 1 indicates less than, and 1, 0 indicates greater than. It means that A is greater than B. Now, because we only have 2 bits, 2 state bits, so I'm going to define the state here with 2 bits, bit 1 and bit 0. And the next state will also have 2 bits. Okay, so we always here declare the state, the present state, as well as the next state. Notice that these are registers. That means actually these are variables, and we can change their values inside the always statements. The first always statement is going to describe the flip-flops. So I'm describing here flip-flops that are triggered at the positive edge of the clock, but also they have an asynchronous reset. So notice that now reset appears in the sensitivity list of the always statements. So at the positive edge of reset, if we are resetting, we can change the state back to 0, 0. That's my reset here. Okay, it's going to take me back to state 0, 0 at any time, even without the presence of the clock cycle. This is why it's called asynchronous reset. And this is why we have to have the positive edge of reset in the sensitivity list of the first always statement. Now, if reset, then state becomes 0, 0. That's if we have a reset. Otherwise, else state becomes next state. It's very simple. So we are describing here 2D flip-flops because we have 2 bits for state and next state. So we are describing 2D type flip-flops with this always statement, which is sensitive to the positive edge of the clock, and also it is sensitive to the positive edge of reset. Next, I need to describe my next state logic. The next state logic is combinational, so we write it like this, always at star. So therefore, it will be sensitive to all the inputs that we are using inside the always statement. Notice that I'm using state. Here, notice that I'm using A and B. Okay, we don't really have to write them inside the sensitivity list. You just write star because you recognize that the next state logic is combinational. Okay, let the compiler to write all of these, expand this star into all the inputs that appear inside the always statement. So it's going to replace the star with a state, with A and with B. So there is no need actually for you to write them, especially when you have so many inputs, and therefore to avoid making mistakes, okay, you just can write it a star, recognizing that this is a combinational logic. Now, again, we write a case statement. This case statement here, okay, will look at all the possible values of state. We would like to describe the transitions between the states as given in the state diagram. So if state here we have 0, 0, we have 0, 1, and we have 1, 0. These are the 3 states which are shown in the state diagram. Now, because we are using 2 bits to represent state, we can actually also have, okay, the default case here, which is 1, 1. There is actually one state which is unused, which is 1, 1. Okay, so we are representing it here with the default case. Now, if I am in state 0, 0, that will be actually here my reset state, and the inputs here, so my next state will depend on the value of A and B. So if A and B are 0, 1, then my next state must be 0, 1. So I have to make a transition from state 0, 0 to state 0, 1. So this is why I have to write here that my next state will be 0, 1 if the input is 0, 1. Else, if AB is equal to 1, 0, then I have to make a transition from 0, 0 to 1, 0. That's if my input AB is equal to 1, 0. So if AB here is equal to 1, 0, then my next state will be 1, 0. Otherwise, if it is 0, 0 or 1, 1, I have to make a transition from 0, 0 back to itself. So this is why I have to write here 0, 0. So I'm using here a conditional expression to describe my next state based on the present state as well as my input A and B. Now, if my present state is 0, 1, then my next state, if I am here in 0, 1, then my next state will depend on the input AB. If AB is equal to 1, 0, okay, So this will take me from 0, 1 to 1, 0 if the input is equal to 1, 0. It indicates that A is greater than B. So therefore, we make a transition to 1, 0. Otherwise, if you have 0, 0 or 1, 1 or 0, 1, you remain in the same state, which is 0, 1. Similarly, if you are in state 1, 0 and the input AB is equal to 0, 1, you make a transition from 1, 0 back to 0, 1 if the input is 0, 1. Otherwise, you remain in the same state, which is 1, 0 if the input is different from 0, 1. So you remain in the same state, which is 1, 0. In the case of the default case is for the unused state, which is not really shown in this Moore state diagram. The next state must be 0, 0. If for some reason you enter, okay, this unused state, okay, you should make a transition immediately back here to the state 0, 0. So this second always statement describes all the transitions between the states. Notice I did not write any equation, okay, for the next state. Okay, so I did not really write any equation for the next state. I just described them with a case statement according to the transitions that are shown in the state diagram. Finally, for the output logic, the output turns out to be very simple. I have three outputs. I have greater than, which is actually this first bit, and then we have less than, and then we have equal. Notice that greater than and less than are identical to my present state. So if I am actually in state 0, 0, then greater than will be 0 and less than will be 0. If I am in state 0, 1, then greater than will be 0 and less than will be 1. If I am in state 1, 0, greater than will be 1 and less than will be 0. The third bit here is for equality. So equality means that if you are not greater than, okay, so not between parentheses greater than or less than, okay, we can just use a NOR gate, then this is the meaning of equality. Notice that I'm describing here my output logic using continuous assignment. That's one way of describing the outputs. Another way is to use an always statement. A third always statement can describe the outputs greater than, less than, and equal. But if you use an always statement, you have to use a procedural assignment, not continuous assignment. Now we can write a test bench for the Moore comparator. So this module, which is called Moore comparator TB, TB means test bench, is used to test the Moore comparator. So what we have to do is that we have to instantiate the Moore comparator. Okay, so this is my test instance. It has 4 inputs, A, B, clock, and reset. These are the 4 inputs for the Moore comparator. Now notice that these are of type register. Okay, A, B, clock, and reset. We need to have them of type register because we're going to change their values. These are variables, okay, that we need to change their values inside this test bench. There are 3 outputs, greater than, less than, and equal. And these are just simply wires, and we need to watch their values. So what we have to do is that we have to apply a reset pulse initially. So this is done once. I can do this with the help of an initial statement. So the initial statement here, we can write, okay, we have an initial block here surrounded by begin and end. So we can have reset is equal to 1 after 2 time units, and then we can reset it back to 0, right? So we can actually have reset is equal to 1, and then we can have reset dropping from 1 back to 0 after 4 time units. So this is my reset pulse. So reset is going to jump to 1, and then it's going to drop back to 0. We do it only once. This is why I'm using the initial statement. The clock will be generated exactly the same way as we have done before. So we're going to initialize the clock to 1 using this initial statement. And every 5 time units, I'm using an always statement to invert the value of clock. Now, because I'm inverting it every 5 time units, then the period will be equal to 10 time units, as we have seen before. Finally, I have to generate my input test sequence. I have to generate here the values of A and B so that we can compare A with B. So initially, A and B will be 0, 0. Okay. And then after 12 time units, I'm making AB to be 1, 1. Notice that I'm using 12 to have the value of A and B changing after the rising edge of the clock. Okay, so basically the input is going to change after the edge of the clock. Then another 10 time units. Now, since here we are shifting it after the time, after the rising edge of the clock, all the changes here, we are using 10 here or multiple of 10, so that all the changes in A and B will appear after the rising edge of the clock. So I'm going to change it here to 0, 1. Okay, A will be equal to 0 and B is equal to 1. Then to 1, 1. Okay, it means A is equal to 1, B equal to 1, and so on. So we can actually apply an input test sequence, okay, for A and for B. And then we can watch, okay, what will be the value of a greater than, less than, and equal. We can also observe how the states, we look at how the transitions between the states. Okay, so that's how we write the test bench. Once you have written the test bench, then you can simulate it using any simulator. Here I'm using the Model Sim simulator. I have my inputs, which are reset, clock, A, and B. These are my inputs. And I have my outputs, which are greater than, less than, and equal. And in addition to these, I also have a state that appears at the bottom. This is the state of the flip-flops. Now, initially, I have to reset. So I'm going to use here a reset pulse. That's my reset input. Okay, so notice that at t equal to 2 nanoseconds, that my time scale is in nanoseconds. So at t equal to 2 nanoseconds, reset is going to jump to 1. And then after 4 nanoseconds, it's going to drop back to 0. So my reset pulse is only 4 nanoseconds. So this is going to reset the state. It's going to force the state to become 0, 0. That here is my state, which is 0, 0. Now, when the state is 0, 0, then it indicates equality. So the equal output is going to jump to 1. Notice that the greater than is equal to 0 and less than is also equal to 0. Now we can start applying some inputs here, A and B. Notice that A and B are bit serial. We provide here 1 bit of A and 1 bit of B each cycle, starting at the least significant bit of A and B and moving toward the most significant bits. So initially, okay, the value of A and B are 0 and 0, as indicated in the timing diagram. That's my initial input for A and B. Now notice that A and B are going to change after 12 nanoseconds. Okay, so at t equal to 12 nanoseconds, A is going to become 1 and B is going to become 1. We do the change in A and B after the positive edge of the clock. So we never do the changes at the edge of the clock. Now, A is equal to 1, B is equal to 1. That also indicates equality. So the state will remain 0, 0 during the cycle. Okay, notice that's going to remain 0, 0. Okay, and then you can see that the equal output will remain 1 during all of this time. Greater than will remain 0. Okay, and less than will remain 0. Now later we can change the value of A to 0 and B to 1. So when A changes to 0 and B changes to 1, at this rising edge of the clock, okay, it's going to see that A is less than B. So therefore, the state is going to change from 0, 0 to 0, 1. So when the state changes from 0, 0 to 0, 1, this will change the less than output to become 1, indicating that A is less than B. Notice that the greater than will remain 0, and the equal is going to drop from 1 to 0. So they are no longer equal. It indicates that A is less than B. Now, when A jumps back to 1 here, okay, and B remains 1, so this indicates equality after less than. It will remain in the less than state for another cycle. So even though A and B, the most significant bits actually are equal, the previous bits actually were not equal. A was less than B, and therefore we remain in the same state, which is 0, 1, indicating that A is less than B for another cycle. Now notice that after that, okay, A is going to remain 1 and B is going to drop to 0. So during this, so just before this rising edge of the clock, A is equal to 1, B is equal to 0. So therefore the state is going to change to 1, 0, indicating that A is greater than B. So the greater than output is going to jump to 1, less than is going to become 0, and equal is 0. So this indicates that A is greater than B. So we can continue like this, and we can trace the, we can watch the outputs, we can trace the changes in the state, and we can verify the correctness of the Moore sequential circuit, the Moore comparator. In my next video, I will show you how to model registers and counters. That's it for this video. Thank you for watching.